Now we've gone to the crux of this unit, which really is on the topics of internal energy and the first law of thermodynamics. First off, let's review what exactly we already know about internal energy. So if we have some box here that contains a gas, all of the particles of the gas are going to be moving at a variety of velocities in random directions. And according to the kinetic theory, remember, each individual particle can only possess kinetic energy because there are no intermolecular attractions here. So the only way these particles impact each other or the walls of the container is if they impact each other. Additionally, we already learned that the average kinetic energy of these particles correlates to the temperature of the gas. In fact, that's essentially what the definition of temperature is. So we know for a fact that the average kinetic energy of any of these particles has to be tied into temperature somehow. But what exactly is the exact relation here? Well, first off, we have this, that for a single particle, and that single is very important, for one particle, the average kinetic energy we know will be 1/2 mv squared. But it's not going to be just any old velocity. And we might be thinking, okay, well, all of the particles, we're going to assume have the same mass. And we might be thinking, well, won't it just be the average velocity squared? There's actually a very specific term we have for this, which we call the RMS velocity, the root mean square velocity. We'll talk about more of that in a second. But this whole connection here, so this is just the equation for kinetic energy, ties into another equation, which is 3/2 kBT. And this all here are multiple ways of writing out the equation for a single particle's average kinetic energy. So for the average kinetic energy of a single particle, it's in joules, 1/2 mv RMS squared. We'll talk about that in a second. And we have this equation of 3/2 times the Boltzmann constant times the temperature of the gas. And you might be thinking, well, this kind of came out of nowhere. Like, where is the connection here? Why did this just arise from that? And that's a really good question. Unfortunately, the proof of this particular equation is very long and very complicated. And I will do it, but I'm going to do it in a separate video because I never like to give you an equation that we don't have an explanation for, but it would take up just too much time here. You are welcome to watch that one to get that additional background. You are fine if you don't, but I at least want to give you that option. So let's take a real brief second and talk about what exactly we mean by the RMS, or the root mean square velocity. Root mean square is really just a statistical technique for taking an average in a slightly different way. So let's think back to our box for a second. So if we have two particles, one moving with velocity v and one moving with velocity negative v, well, if we average those together, well, what would happen is you would get an average velocity of 0, because v plus minus v is 0. And if I stuck that into the kinetic energy equation, 1/2 mv squared, well, then we would get an average kinetic energy of 0. Now, that doesn't make a whole lot of sense, because the particles are moving. They definitely have kinetic energy. So instead, we ignore that, and instead use something called the root mean square velocity. And the idea here is that we take each individual velocity, so like v1 and this other velocity v2, and we square them both. And by squaring them, we get rid of the negatives. And we do this for however many we have. And then we divide them by the total number. So essentially, we are now taking an average of all of the squared v's. And when we are done, we just take a square root of the whole thing. It's a different way of calculating average, and it won't get the exact same value as an average, but it will be very, very close. But it allows us to ignore the positives and negatives and just focus on the positives. So VRMS is equal to the square root of the average of the v squared value. So essentially we are taking the average magnitude of particle velocities. That's a way to think about it. Now, we're not going to have to use this equation very often. I really want you just to be familiar with the term because you're going to see it used periodically, and I don't want you to freak out because you've never seen it before. As a brief note, if we were to graph this on a Maxwell-Boltzmann distribution with the number of particles and the speed in meters per second, remember that peak is the most probable. If we were to take a random molecule of this gas out at random, odds are it would have this velocity. The average velocity we talked about was a little bit higher, but VRMS is actually even just a tad bit higher. Even so, we can think about it as simply another way of doing the average. So at this point, we found a way to connect the average kinetic energy of a single particle in the gas to the gas's overall temperature. We just multiply it, the temperature, by the Boltzmann constant, and then times 3/2. And by doing that, that allows us to figure out the energy of a single particle. So the hotter it is, the more kinetic energy that will be. But how often do we really deal with one particle? Not very often. We really care much more about a system of particles. So if we want the total kinetic energy, we have to multiply this average kinetic energy by the total number of particles. And so if we do that, I can stick this equation in and we'll get 3/2 in Kb, the Boltzmann constant, times the temperature. But as a quick reminder, we already talked about the fact that the number of moles, so moles is little n, is equal to the number of molecules divided by Avogadro's number, where Avogadro's number is 6.02 times 10 to the 23. So if I want to do this, if I want to substitute in for n here, I can rearrange this. So I get 3/2. Instead of having n, I'm now going to stick in n times Avogadro's number times Boltzmann's constant times the temperature. But, once again, like in a previous video, we talked about how these are both constants, and we can actually combine these into a single constant, R. So in other words, K total, the total kinetic energy in this gas is really just 3/2 times n, the number of moles, times the ideal gas constant, times the temperature. So once again, we want to think about this from both a macroscopic and a microscopic perspective. When we're talking about the internal energy of a gas, which we abbreviate with a U, from a macroscopic perspective, what we really mean is the thermal energy. We're ignoring all other types of energy, so this is just saying what is the thermal energy contained in this gas. But on a microscopic perspective, that is the total kinetic energy of all of the particles. We don't think about individual particles as having thermal energy. They all have kinetic energies that when you combine them all together, form this disordered thermal energy. Now there are many different ways, as we just saw, to calculate this. We've got many different relations. So we have the internal energy is equal to the number of molecules times the average kinetic energy of a single particle, which is the same thing as 3/2 n times Boltzmann's constant times the temperature. And lastly, this is also equal to 3/2 times the number of moles times the ideal gas constant times temperature. One key thing we want to make sure remember, these temperatures must be in Kelvin. If they are not in Kelvin, this equation will not work. Additionally, this only works, this equation is only appropriate when we are dealing with ideal gases. But as long as we're sticking in the realm of thermodynamics with the kinetic theory, that was one of the assumptions we had to make. So this equation is therefore totally appropriate. Well, if we think back to AP Physics 1, whenever we dealt with thermal energy, we always thought to ourselves, man, that's just energy we've lost, right? Seemed pretty useless. So we might be thinking, well, why do we care so much about thermal energy? That's a good question. So once again, let's look at this box containing these particles of gas. Well, if we look at this, let's change this a little bit by making one of the walls of the box able to move in and out. We can pretend it can slide in and out, and this essentially has become now a piston, because one side of the box is free to move. Well, initially, if the pressure of the gas inside the box matches the pressure of the atmosphere, well, those pressures combined are going to each have, remember pressure is force over area, So we're going to have a force from the atmosphere pointed in, a force from the gas pointed out, so this piston head is going to just stay at rest. Nothing's going to happen. But let's change things up a little bit. Let's start heating this gas up. Well, when we heat this gas up, we know for a fact that the temperature is going to rise, and if the temperature rises, the pressure is going to rise. So now the pressure of the gas will be greater than the pressure of the atmosphere, which means that the force of the gas will be greater than the force from the atmosphere. And therefore, the piston head will start to move. Another way to think about this is on the micro scale. If any of these particles hit the wall, we talked about how all these collisions are elastic. So if a particle hits the wall, it bounces back at the same velocity. But if it hits the wall that can move, it is still an elastic collision. No energy is lost. But when it hits the wall, some of that momentum will be transferred to the wall, and some of the momentum is transferred back to the particle, but it's not going as fast as it did originally. So some of that kinetic energy, it's not lost, but it has gone to the moving piston head. So in other words, what we have done is we have allowed these gases to apply a force over a distance, which if we remember, if we combine these together, is the equation for, I kind of overwrote this here, mechanical work. This is very, very crucial. This is telling us that if we heat up this gas and allow the piston to expand, we are actually turning thermal energy from the gas into useful mechanical work. Energy that can be used to turn gears and pulleys and rotate objects and turn turbines, etc. And this underlying concept is something that we call a heat engine. A heat engine is a system that converts thermal energy into mechanical work. And we are surrounded by these. Now, back in the 1800s, it was mainly steam engines and things like locomotives, but eventually that started going to car engines and the internal combustion engine, and even to things like most power plants. Any power plant that involves heating up a substance and that substance subsequently turning a turbine is a heat engine that allows us to harness electricity. We'll learn way more about that down the line, but right now we just want to focus on that heat part. The operation of heat engines is governed by the laws of thermodynamics. And the first one of these we learned way back a long time ago, and honestly, it has not changed much in its old form and its new form. We can still understand it pretty easily. So, just to review, the first law of thermodynamics tells us that for a closed system, so a sealed system, in which only the internal or thermal energy changes, that change in internal energy is equal to the energy added or removed as heat, mechanical work, or a combination of the two. So the equation we got for that was delta U, that change in internal energy, will be equal to heat plus mechanical work. And we're going to talk way more about that in a second. But just as a reminder, this is simply a restatement of the conservation of energy. The internal energy of the gas changes, and it can only change because either one, thermal energy is being directly added to it or away from it in the form of heat, or it is doing some form of work and is therefore either gaining or losing energy in that way. The first law of thermodynamics is mathematically pretty darn simple. If we look, delta U equals Q plus W. I mean, there's not even multiplication in this equation. It is pretty straightforward. That's not the tricky part. The tricky part is trying to figure out what do all of the pieces of this equation really mean. And additionally, we want to be really careful with positive and negative signs. So for delta U, as a reminder, is the change in internal energy, which we've already just learned, and we just learned an equation for internal energy, 3/2 capital N kBT, or 3/2 little n RT. So we have this equation, this set of equations, here. But we don't just want U, we want delta U. But remember, this is a sealed gas. The gas is in a sealed container, sealed piston. So we're not going to change the number of molecules or the number of moles, and then R, Kb, and 3/2 are all constants. So the only thing that can change besides U is the temperature. So really, when we're looking at delta U, all that's really telling us is the temperature going up or going down? If the temperature of the gas goes up, delta U, the internal energy, the thermal energy, has increased. If the delta T goes down, well, then the thermal or internal energy has decreased. The next part of the equation is heat, which I know annoyingly we abbreviate with Q. And remember, heat is simply a transfer, a net transfer of thermal energy. So when we're talking about a gas, if we have Q, we're talking about adding thermal energy to the gas directly or taking it directly away. Well, let's first talk about what is positive Q. Positive Q would be heating the gas, making the gas hotter. And there's multiple ways we could do this. You could put the piston over an open flame. You could put the piston on a hot plate. But both of those are a little more dangerous. They're not the safest way to heat a system. The safest way is to stick the piston in what is called a hot water bath, which basically just means we have water here that we are slowly heating up, and that allows the piston to heat up at a more uniform, slow, safe rate. The other way we can change Q is with a minus Q. A minus Q is cooling the system, where we're basically just trying to cool the piston down. And a couple ways we can do that is with coolants or other chemical refrigerants, or additionally, and more commonly and easily, we can just use an ice bath. Just stick the piston in some ice or in some ice water, and the temperature will go down because thermal energy will leave. Lastly, we have the W, which stands for mechanical work. And once again, the W can be positive or negative. First situation. Let's imagine we have our piston, and the piston has molecules moving around, the gas inside, and they hit this piston head, and the piston head is accelerating away, causing the volume to increase. Well, if the volume increases, the gas is expanding. A couple things we need to remember. As we saw a minute ago, for this to move outward, that means the particles in here have to be losing kinetic energy, so the kinetic energy of the particles is going down. So the temperature is going down, and additionally, we know the pressure is going down. So therefore, the gas is losing energy to the surroundings. It's doing energy on the surroundings, so that positive change in volume is actually equivalent to a negative work. The gas is losing energy as it performs this operation. The other way is just flipped. That if I have a piston with the piston head going inward, well, if it's going inward, that's going to be a negative change in volume. And if it has a negative change in volume, the kinetic energy of the particles is going to go up as they speed up, the pressure is going to go up, and the temperature is going to go up as the gas is compressed. And we say that the work is done on the gas by the surroundings. By the surroundings, we really just mean the environment, but a lot of times we don't mean like the whole world. We're just talking about what's immediately around it, so we use this word surroundings. So this negative change in volume is tied into a positive work, because as the gas is compressed, it gains energy. But how exactly do we determine the amount of work? Now back at heat, we don't really have an equation for that. We would just be told, oh, energy is added in this amount of joules or taken away in this amount of joules. But work is a little more complicated. So let's remember how we talked about work in AP1. In AP1, we had this equation that work is equal to the force parallel times the distance. And additionally, we talked about the fact that if we have a force versus distance graph with force in newtons and distance in meters, that if we have some plot here, so the force is not constant, the area under that plot would be equal to the work, which makes sense because if we look at this, so an area, we have one dimension times another dimension. If I look at the units, I have newtons. This unit is meters, newtons times meters. That is literally the unit of joules. Now, you might think, okay, there's got to be some corollary here, and you're not wrong. There's one thing we want to be careful of. There is an equation that's a corollary to this one. However, we're not going to learn that right now, and the reason why is that it only works in certain circumstances. Just like this equation only works when the force is constant, this equation only works some of the time, so we're going to learn it when we get a little more details on what that specific moment is. However, this formation of it always works. That if we take the area under a force times distance graph, that will always be the work, even if the force is changing. Well, we have the same thing here, but we haven't been working with force and distance graphs in thermodynamics. We've instead been working with something else, which are PV diagrams. I know my camera's cutting this off a little bit, but it's the pressure in pascals and the volume in meters cubed. And if we look at this, well, let's look at this area again. And honestly, it makes sense that this area would also be the work, because if we look at the units, we have pascals times meters cubed. But what is a pascal? A pascal is nothing but a Newton per meter squared. And if I've got meters squared and meters cubed, this is going to cancel out until we only have 1 meter left. So I'm left with newtons times meters. Look at that. I have joules once again. However, there's one thing about this that makes it a little annoying. That we really need to pay attention to the sign of the change in volume, delta capital V. For instance, let's look at this first PV diagram here, number 1. And if I look at this PV diagram, if I look at the process here, my volume is getting bigger. So there is a positive change in volume as the gas expands. But remember, if the gas is expanding, it's losing energy, which is equivalent to a negative work. So this area here, we would count as negative as it moves from left to right. So, okay, that's really, really annoying, because usually we think of if it goes to the right, it's positive. This is a bit of a flip. If we have a thermodynamic process that goes from left to right, or a better and more conceptual way to think about it, if we have one where delta V is increasing, that is going to equivocate to a negative work. Now let's look at the flip. I now have a volume that is getting smaller. So therefore the gas is being compressed. If it's being compressed, it is gaining energy. That is a positive gain in work. So we would consider this to be a positive area. So if it's going from right to left, or there is a negative delta V, we must remember that is a positive work. So to know whether or not that area should be counted as negative joules or positive joules, we really need to focus on, is V getting bigger or is V getting smaller? Let's look at an example to try to see the first law of thermodynamics in action. Imagine we have a piston here, and this piston has 2 moles of gas in it, and we're going to say that we are heating it up, and that there is a change in thermal energy, or a heat, of 1,000 joules, and additionally the gas is expanding, so there is 300 joules of work done. Now, before we do anything else, we need to know, are these positive or negative values? Well, if we are adding heat to the gas is gaining energy, so this should be positive 1,000 joules. But if the gas is expanding, it is losing energy to the surroundings. So this should be negative 300 joules, because the work will be negative. Well, now we pull out the equation for the first law of thermodynamics, because we want to know specifically how much does the temperature of this gas change during this thermodynamic process. We know for a fact that it's going to either go up or go down. It's either going to go up from the heat or it's going to go down from the work. And if we look at the two, well, the heat is bigger, so we should expect the temperature to go up. So I have delta U equals Q plus W, but we just learned that if we ever see delta U, we can immediately substitute with 3/2 in our delta T, or 3/2 capital N KB delta T, depending on if we know moles or molecules. And at this point, we have everything. I just rearrange to find the change in temperature, and I know Q was positive 1,000 joules, the work was negative 300, you have to be very careful on is it positive or negative, N was 2 moles, R is the ideal gas constant of 8.31 joules per mole Kelvin, And that gives us, when we stick it in our calculator, a change in temperature of positive 28.1 Kelvin. The gas does indeed increase in temperature. I can't emphasize this enough. The math is not going to be hard here. What is hard is remembering is should it be a positive sign or a negative sign when you're dealing with all the values in the first law of thermodynamics. And this is what you need to remember. If the gas is gaining energy, it should be a positive sign. If the gas in the piston is losing energy, that's a negative sign. So these are the final takeaways for arguably the most important lesson in the entirety of the thermodynamics unit on internal energy and the first law. So at this point, can you, 1, calculate the internal energy of a gas if you know its temperature? 2, can you conceptually explain how heat engines convert thermal energy into useful mechanical work? 3, can we apply the first law of thermodynamics, delta U equals Q plus W, to thermodynamic systems, remembering when every piece should be positive or negative? And lastly, can we determine the work either done on a gas or by a gas from a PV diagram?